Early software engineering viewed problems through a procedural lens. Programmers wrote sequences of instructions that processed inputs to generate outputs in a linear, step-by-step fashion. This schematic illustrates the architecture of procedure-oriented programming, or POP. Here, a list of distinct functions operates on global data. The data moves openly around the system, flowing between functions without any structural protection. Because the data is globally accessible, a single structural change to that data cascades outward. If you modify a shared variable to fix an issue in function 1, you risk corrupting the inputs for every other function sharing that memory space. At scale, tracking these sequential algorithms becomes difficult. The procedural model struggles because it attempts to manage complex logic while leaving the underlying state completely exposed to external interference. C++ offers a different approach to this. Instead of writing functions that pass unprotected data, object-oriented programming partitions memory into secure, isolated units where the data dictates the structure. A class acts as a memory template, a custom data type defined by the programmer. An object is the specific physical allocation of that template in memory during runtime. Inside these objects, state, the data variables, and behavior, the functions, are bound together into a single unit. This structural change reorients the programming process around the design of these data entities, rather than the movement of raw global data. Looking at this basic C++ syntax block for a class named item, we see the internal variables number and cost declared inside the brackets. These variables fall under the private access specifier. In C++, this acts as a strict compiler-level memory boundary, and it is the default state for any class. If an external function, or the main program, attempts to read or modify number directly, the compiler rejects the instruction. The data is sealed off from the rest of the program. To interact with the object state, the class provides communication ports using the public access specifier. Member functions like getData are defined inside the class and have authorization to modify the private variables. This creates a scoping problem. If we define getData outside of the main class brackets to keep the code organized, the compiler needs a way to map that function back to the correct object. The solution is the scope resolution operator. This double colon explicitly binds the external function definition directly back to the item class scope. By forcing all external interactions through these validated public member functions, encapsulation prevents unauthorized data mutation. Securing the data is only the first step. An object cannot be allowed to spawn into memory with garbage values or an invalid starting state. This is handled by the constructor. It is an automated lifecycle hook with the same name as the class that executes at the exact moment an object is instantiated. A default constructor accepts no parameters, zeroing out variables by default. A parameterized constructor accepts specific arguments, allowing the program to initialize different objects with distinct starting values. Constructors also handle dynamic memory allocation. Using the new operator, the constructor calculates the required space and requests it from the heap at runtime. But dynamically allocated memory must be explicitly released when the object scope ends, or the program will suffer memory leaks. This is the job of the destructor, marked by a tilde symbol. When the object reaches the end of its scope, the destructor automatically invokes the delete operator. This releases the specific blocks of heap memory back to the operating system. Paired together, constructors and destructors provide automated control over the memory lifecycle, ensuring state is always valid and resources are always returned. Strict encapsulation creates a structural dilemma. Sometimes two distinct objects must interact closely without exposing their private data to the entire system. Consider a manager class and a scientist class. Both contain private salary data, and both need to be processed by a single income tax function. The function is trapped outside their individual memory boundaries. C++ resolves this through the friend function. By declaring a specific function as a friend inside the class, the programmer explicitly overrides the default private boundary for that entity alone. A friend function is not a member of the class. It cannot be called using an object's dot operator. It is a standalone entity granted highly specific access clearance. To authorize this, the class must include the friend keyword inside its own definition block. The permission must be strictly granted by the class itself. It cannot simply be seized from the outside by a rogue function. While C++ defaults to rigid data security, friend functions provide the mechanism for necessary interclass operations without dismantling the system's defenses. As software grows, engineers need to reuse and extend an object's capabilities without rewriting existing code or breaking the base structure. This is inheritance. A new derived class, like manager, absorbs the properties of an existing base class, like worker. This forms an ISA relationship. A manager is a worker, but with additional features. However, inheriting a class does not automatically grant the derived class permission to bypass the base class's private boundaries. Memory protection remains in force. This matrix governs the inheritance of access levels. Depending on whether the derivation is public, private, or protected, the visibility of base class members changes. Crucially, private base members remain locked. Even the derived manager class cannot directly access the private data members of its own worker base. To allow for controlled extension, C++ utilizes the protected access specifier. A protected member is private to the outside world, but fully accessible to any derived class. Inheritance allows systems to scale by layering new capabilities while strictly enforcing the foundational data boundaries of the original code. Comparing the original procedural structure on the left with the C++ model on the right shows a fundamental change in how state is handled. C++ processes complex background operations invisibly. Abstractions like operator overloading allow these encapsulated objects to interact as simply as raw integers. The architecture relies on three pillars: strict data hiding to prevent unauthorized access, automated constructors and destructors to manage memory lifecycles, and inheritance to safely reuse structural code. Together, these mechanisms address the vulnerability of global state that compromised early procedural logic. The final result of object-oriented design is a system that manages its own complexity through self-contained units communicating over defined paths. Ultimately, object-oriented C++ replaces the need to manually track global variables with a system of independent, self-governing data entities.